Hi everyone. Welcome back to the third day of the F equals MA club. This is in the online lecture for the day three of our F equals MA club, as well as just some worksheet problems and answers. And this is going to be for conservation of energy. I'm pretty sure today's going to be a slightly shorter lesson, just because there's not really too many concepts that I can cover right now. So just a little bit of review. Last time we talked about dynamics, where we had F equals MA. Remember that our two main ones were circular motion and inclined planes. We also talked about some F equals MA like exclusive strategies, which are dimensional analysis, error propagation, and just some basic strategies, such as just breaking hard problems down, solving for limiting cases, and not to overcomplicate problems, but not to be tricked by easy answers. And if you have any questions or if you don't understand some of this, you can go back to the video from last time. And if you still have any questions, just let me know. Alright, so let's move into energy. The big thing is we have two types of energy that we're going to be talking about right now. We have potential energy and kinetic energy. Remember that these two add up to get your total mechanical energy. For now, we have two different forms of potential energy. We have gravitational potential energy, which is going to be mgh. We also have our elastic potential energy, which is going to be for springs and stuff, and that's going to be 1 over 2 kx squared. And remember that our kinetic energy is going to be 1 over 2 mv squared. Of course, we're going to get into other ones as well. We have our rotational kinetic energy. We have potential energy of gravity overall. But for now, these are going to be the ones that we're going to be talking about. So the big thing that we need to know for the F equals MA competition is conservation of energy, where your initial kinetic energy plus your initial potential energy equals your final kinetic energy plus your final potential energy plus any non-conservative work. So what that would mean is, let's just switch over here. So if we have an initial kinetic energy, let's say we have a ball on top of a hill, right? Oh, we have a ball on top of a hill. At this point, there is no kinetic energy, right? At this point in time, there is no kinetic energy, so your kinetic energy would be equal to 0. Let's say that this is, let's say that this is your height. Ooh, even that's bad. Let's say this is your height, and your ball has some sort of mass, right? So your potential energy, in this case, would of course be equal to mgh, right? At the bottom of this hill, your ball would now have no potential energy, right? There's no potential energy, but there is a lot of kinetic energy. All your potential energy is now converted to kinetic energy in a perfect world, where your kinetic energy will now be 1 over 2 mv squared. Your potential energy would be equal to 0. And if you were to just solve for this and say there's no friction, there's nothing about rolling, that would mean that your total amount of energy, which is your total mechanical energy, is going to be equal to your initial kinetic energy plus your initial potential energy equals your final kinetic energy plus your final potential energy. Since we have no final potential energy and we have no initial kinetic energy, what we can say is that our total mechanical energy is going to be equal to our potential energy, our initial potential energy, which is also equal to our final kinetic energy. And that little WNC, that just means non-conservative forces. So in our case, and typically it would be something about friction. For some problems, it might be something about air resistance, air friction, or it's something like this, plus something like that. That's most likely not going to come up too much, and it's not going to be important for the time being. So let's say we do have some form of frictional force here, like mu kn or something like that. That would add into our non-conservative forces. So the amount of work that whatever your frictional force does here is going to be applied to here, right? Yeah, so that's what this conservation of energy stuff means. And if you understand it, good for you. I'm just covering it for anyone who doesn't understand. All right, so let's move on. So just some other relations that are really good to remember. You can search these up on your own if you're unclear with them. Remember that work equals your force times your distance times cosine theta. Your average power is going to be your work over time, and your instantaneous power is going to be the force times velocity. Remember that work is also the total amount of work is going to be the total change in kinetic energy, and your non-conservative work is going to be the total change in mechanical energy. So if you have friction, remember that all the work that the amount of work that friction does is going to be the total change in mechanical energy if you don't have any other non-conservative works. And so just calculus addition, we have work equals the antiderivative of force, dr. We have power is a derivative of work, average power. Your total work is your derivative of your kinetic energy, and your potential energy. Oh no. Your potential energy is going to be the negative antiderivative of force. This is just an optional problem. If you really do want a solution to it, just let me know. But for now, I'm not going to cover it, and I'm just going to get straight into the problem. So the first one states that a block with mass m is released from rest at the top of a frictionless ramp. This is very similar to the problem that we talked about for the last class, with the block sliding down the first ramp and going up the second ramp. I really should have included that problem in this worksheet, not the other one. But remember, I did that one in a very short amount of time on a lot of drug. No, I'm kidding. But that was just not a well done one. We're just gonna do this one. So the main difference is the frictional force is only on the second ramp, right? So if both ramps make an angle of theta with the horizontal, to what height above the base above the second ramp will the block rise? So let's start working on this then. So yeah. All right, let's get our let's get our handy dandy little line tool out, because I'm bad at drawing. So let's say we have a ramp here, right? We have one ramp here, and then this goes up to yet another ramp, right? We have a second ramp here, and we have a mass here, right? And we're assuming, like, of course, this doesn't look logical. You might say, oh no, once it goes here, it's just gonna ram, topple, and then fly out into the sky or something like that. It just doesn't matter. The entire point is just a conservation of energy thing. So we start at a height of h1, right? We start at a height of h1 here. This is h1, and then we rise to another height of h2, right? We have a mass m. This is h1. This is h2. This is the ramp that has the friction, right? What's it labeled? Is it labeled mu k? Let me just double check. Yeah, mu k. So, so this has a frictional force of this has a friction coefficient of mu k. Remember that both of these have the same angle, right? Both have the angle theta. And so to what height? So it's just trying to find h2. So last time we talked about how we can do this in a dynamics approach. Today we're going to talk about it in a conservation of energy approach, right? So first things first, our frictional force is only going to be apparent on this ramp, right? So the amount of non-conservative work, right? Our non-conservative work is going to be equal to our force, right? Our frictional force times our distance, right? Plus a cosine theta. Right? So our distance is going to be, so first of all, our frictional force is going to be equal to, what is this? So our frictional force is equal to mu kn, right? Normal force, what's our normal force going to be? It's going to be, and for this case, I'm just going to remove this. We technically don't need it. I would explain why, but I'm too tired to do so. So, we have our frictional force, right? Our normal force is going to be mg cosine theta, right? Because of the components, right? So our normal force is going to be equal to mg cosine theta. So that means our frictional force is going to be mu k mg cosine of theta, right? So we can plug that back in here. So that's going to be mu k mg cosine of theta. And here's where our so what's our distance going to be? So our distance is going to be we have h2. And so how would we try and find our distance here, right? This is our hypotenuse, this is our opposite. So we can just take the sine and have h2 divided by our sine, because sine is equal to our opposite over hypotenuse, right? So if we have our opposite divided by our sine, which is going to be our opposite over hypotenuse, that's going to be equal to our opposite times our hypotenuse over the opposite. These cancel, so we get our hypotenuse from there. So that's how we get this is going to be equal to mu k mg cosine theta times h2 over sine theta, right? And I'm just gonna do this. Select all. No, I'm bad at this. Just take this. No, I don't want to rotate this. Here. Let's make it that small. Oh, ooh. Okay. Please work with me. There we go. Good. Okay. So now we have our big thing, which is our non-conservative forces. Is equal to our mu k mg cosine of theta. Cosine of theta times h2 over sine theta, right? So let's plug that into our conservation of energy equation, right? So we have no kinetic energy here, and once we reach the top, the maximum height of which the block will reach, it'll also have no more kinetic energy, right? Because it's stopping. That's the maximum height. So our equation is going to look like this. So we have our initial kinetic energy, right, plus our initial potential energy is going to be equal to our final kinetic energy plus our final potential energy plus our non-conservative forces, right? The amount of work done by non-conservative forces. We have no kinetic energy initially and in the final stage. So our initial potential energy, remember that is going to be mgh h1, right? This is our first height, is going to be equal to mg h2 plus our non-conservative forces, which is going to be mu k mg cosine of theta times h2 over sine theta, right? And okay, so the reason why there's no cosine theta here, if you really want the explanation, is even though we're moving at an angle here, if we just envision like if we just rotate this this triangle like in this direction, so it looks something like this or something. Oh no, so it looks like that, right? Our force is in this direction, right? Oh well, no, our force is in this direction as our block moves up the ramp, right? This is the direction that our force goes in, and so technically the force and whatever, like it's parallel to where it's like its direction of motion, right? Well, like close enough. I have bad explanations. Yeah, sorry. But the entire point is these are on the same plane, so it's technically going to be cosine of 0, right? No, not that. Cosine of 0, or you can say like cosine of 1. No. You could also say cosine of 180 or something like that. These are both going to be 0. They're going to be 1. They're going to be 1. I'm smart. Okay. Sorry. Long day. Oh. This is a train wreck. But back to the thing, right? We have this whole thing going on. So we're trying to solve it for h2, right? So we can factor this out. We can also cross out. Oh no. We can also cross out all of these mg's, and we can factor out this these h2's, right? So what we can say is that our h1 is going to be equal to h2 times 1 plus our cosine, our mu k cosine theta divided by our sine theta, right? That seems like it, and then not yet, but now we can basically just divide both sides by h2. Oh wait, no. Why am I having a brain fart? We can redo this as h2 is equal to h1 times h1 divided by 1 plus mu k cosine theta over sine theta, right? where we can say that because we can just divide both sides by this whole thing, right? And then we get H2 on its own. So that seems like a good answer, right? Yeah, it is a good answer. Problem is, none of our answer choices follow that. But we can see that all of our answer choices have a sine theta in front of them, right? Where we have H1 sine theta. So, going by that logic, I know how to move this. Oh no. Going by that logic, right? Going by that logic. Please let me move. Thank you. Don't mind that. Going by that logic, we can say that we can just multiply this side by what is essentially 1, right? Times sine theta over sine theta. And this is technically 1 over 1, right? So we can say that H2 is equal to H1 sine theta divided by sine theta times 1 is sine theta plus mu k cosine theta divided by sine theta times sine theta is going to be mu k cosine theta, right? And if we look back on our slideshow, not our slideshow, our work, we can see that that will be our answer choice A, right? Okay, next one's pretty simple, right? A point mass m is connected to an ideal spring on a horizontal frictionless surface. The mass is pulled to short. Which of the following? Basically, just like a graph of the energy, right? All right. Let's just let me. Please let me move. Oh no, this is rotated now. I don't care. Okay, let's go back. So okay. I'm sorry, I'm having a bad day, guys. So let's go back here, right? Let's select this and go here. That's way too big of a brush size. Okay, so let's start, right? So we get multiple plots. We have a. Let's just do. Oh no. Let's just do this, right? And then we have another. I'm very good at drawing lines, if you couldn't tell. So let's just think about this, right? We have one. Oh no. We have one that's. Why is it? Okay, I don't even care anymore. We have. One that's a circle, right? Thank you. We have one that's a circle, one that's a diamond, one that's like a little weird parabola thing, right? We also have one that actually has like good lines, and then we have one that looks like this, right? Where this axis is going to be our kinetic energy, and this axis is our potential energy, right? And I'm going to just zoom out a little bit more. There we go. So the key about this is, okay, let's just imagine this, right? Let's say we have our little graph here, right? We have our little straight line graph. And let's say that our total mechanical energy is, our total mechanical energy is going to be, I don't know, 2 joules, right? So if that were the case, that means that this point here is going to be, what, 0, 2? Where we have 0 joules of potential energy and 2 joules of kinetic energy. For this point, it's going to be 2, 0. I think you get the point where we have 2 joules of potential energy, 0 joules of kinetic energy. And so this point will be 1, 1, and then we can have multiple other points. It doesn't matter. The big thing is if we go to the negative side, let's say we choose this point, right? And this is 1, this is -1, 1, right? That would mean we have a potential energy of -1 joules, right? We have -1 joules of potential energy, and we have 1 joule of kinetic energy, right? Problem with that is, remember that our whole thing is that our mechanical energy is equal to our potential energy plus our kinetic energy, right? So for all of these on this quadrant, right, over here, that's true, where we have 2 plus 0 is equal to 2, 1 plus 1 is equal to 2, 0 plus 2 is equal to 2, and da-da-da-da-da. All of these satisfy the fact that the total amount of E is 2 joules, right? Problem with the negative quadrant is that now we have -1 joules plus 1 joules is not equal to 2 joules, it's equal to 0 joules. So anything in this quadrant isn't going to work. Same thing goes for this quadrant and this quadrant, right? So the only quadrant where like that rule is satisfied is in this one, right? Quadrant 1. And the only answer that has only that quadrant filled out is going to be our answer choice E. And so it's going to be E. It's quite simple. It just takes a little bit of thinking. All right. Oh, this is the flipped one. Okay, I'm sorry. All right, so now we have the 3 free responses, right? We have the following graph of potential energy is used for questions 18 through 20, and this is 18 through 20 if you couldn't tell. So which of the following represents the force of the given potential, right? Okay, so let's start working on this then. So let me first take a screenshot, make my life easier, right? So we can just do that here, paste that here. Oh no. Okay. Sorry, I've got some technical difficulties. I'll be right back with you. Oh no. Can I please? There we go. Okay. There we go. All right. Sorry for the wait. Your order is now ready. So we have this graph, right? We have this graph and potential energy here, and we have our position there, right? I'm gonna make my brush size small. Is that good? That's good. Okay, so which of the following represents the force to the given potential? Remember those calculus equations that I was talking about? Yeah, so our potential energy, which is U, right, is going to be equal to our negative antiderivative of force dx, right? So our force is then going to be equal to the negative derivative of our potential energy, right? Dx. And so that means that we just need to find the negative derivative of this graph, right? Because this is already labeled by position. So the only one that satisfies that, so let's see, right? So this has a slope of, from what I can tell, this is a slope of -1, right? And this is a slope of +1, right? So since this is a negative derivative, we're going to be having a graph that starts from 0, right? It's going to have a slope of 0, and then it's suddenly going to have a reading of 1, right? Because the slope is -1 here, and it's a negative derivative, so it's going to be 1. And then it's going to drop down to -1, right? Because slope is +1, a negative derivative of that is going to be the slope, which is going to be -1, right? So your graph's going to look something like this, where it's going to be 0, 1, and -1, right? So the only option that satisfies that is going to be E, right? So that's our answer. All right, let's go back here, right? So, oh god, okay, that's a lot more work to do. So, give me just one moment. So I'm gonna keep this here at all times. Sorry about the wait. All right, and so the next part of our problem comes in now. Oh no. Please move. Please. Oh no. Oh. Okay, let's move this here. All right. Okay. Sorry again. Now we are on to problem 19, right? Okay. So, let's go to our brush, right? So, consider the following graphs of position versus time. Which of the graphs could be the motion of the particle in the given potential, right? So, the big thing is that our x is now in the y-axis, right? Our position is now in the y-axis instead of the x-axis. This is our potential energy before. Now this is time, right? So, our basic thing is we're just going to try and analyze where the position is and see if it matches up, right? So first thing that we can rule out, and most people rule this out very quickly, is it can't be number 2. The reason for that is the x position is -5 here, right? And we know that our potential energy is changing, which means that our force is also changing, right? Which means since force equals mass times acceleration, and hopefully your mass is not changing, this is going to be a constant, that means that your acceleration is changing, which means that your position is going to change. Remember, acceleration, velocity, and position are all related to each other. So that means that our second one is already wrong, which means that this can be ruled out and this can be ruled out. And here's where a lot of people got stuck, right? First things first, we can tell that our first graph is going to be correct, right? Because if we look at our position at 15, right, that's going to be over here, we have no change. Oh, not that. We have no change in our potential energy, right? Which means we have no acceleration. Which means that this is a valid choice, right? So, yeah, so we can roll out this. Now it's the final one. It's graph 3. And a lot of people thought that this was not valid because this is changing, right? And it's clearly not changing here. Problem is, it kind of is. So the thing is, right? Since we have no potential, we have no change in potential energy, right? So du equals 0. That means that our F is going to be 0, right? Our F is going to be equal to 0, which means that our A is equal to 0 because we still have a mass. The problem about A being 0 is that you can still have a velocity. Your velocity can still be a constant, right? Which means that this is valid because like the only way that this wouldn't work is if it were doing something like that, where that would mean that the derivative of that would be would have a positive acceleration, right? This is a 0 acceleration, but this still has a constant velocity, right? Because this is a position graph. So that's why we can say that both 1 and 3 are correct. So this was a kind of tricky problem, but in the end, quite a lot of you got it. So yeah, good job. So on to our final problem, which is the little sine graph looking thing, right? So let's first erase all this. Let's remove that. Let's go back here. Thank you, screen snip, snip and sketch, whatever you're called. You've been very helpful and also very bad at your job. Let's also copy this over. Let's put that here. And then what we can do is we can use this tool, move this over, and our lesson can resume. Okay, let's move this down, that here. And now, on to our final problem. Consider the following graph of position versus time, which represents the motion of a certain particle in the given potential, right? So the maximum position that we reach is going to be 5 and -5, right? Both of these are going to be our max, right? So that means that our maximum potential energy is going to be at those positions, right? Our maximum potential energy at those two positions, if we look on our little graph here, we can see that the maximum potential energy is at -5 joules. So the total energy of the particle is going to be -5 joules. Because remember, yeah, that's just how it's going to be, right? So this is our total energy because we have no kinetic energy there. So the total energy of the particle is going to be -5 joules. So that's it for the worksheet. I know it was a little bit shorter than last time, but I didn't want to do too much this time. We're probably going to have like a little thing at sometime in the future, like a little test with a lot of material for the past 4 lessons. Past 3 lessons, maybe even more. But yeah, thank you so much for attending, and hope to see you next week. Bye.